Here at the end of both lectures 29A and 29B, we're going to be transitioning into the home stretch of this course on differential equations and linear algebra. My aim is to finish by lecture 36. In 29A, at the very end, we're talking about linearization of nonlinear systems. That's a big topic here at the end of the course. We will also talk about Laplace transforms. And at the end of lecture 29B, we're going to focus on orthogonality again, which we've talked about before, but now we're really going to get more in depth and ultimately get into some applications of that in the lecture Bs. So let's start by reviewing what we learned from lecture 28A, here in lecture 29A, reviewing sinusoidally forced harmonic oscillators. You will definitely benefit from watching 28A first. That's a much more symbolic approach than what I'm going to show you here. I will show you plenty of symbols, but I'm not going to show you a ton of details. Then we're going to look at some pretty cool graphs and think about the physical implications of those graphs, as well as rounding off our understanding of what's going on, in particular when the forcing function frequency is the same as the natural frequency of the oscillator. So here's our ODE, second derivative of y with respect to t, plus p times the first derivative, plus q times the function itself. That's the left-hand side. It is a forced equation. We're going to have cosine of omega t on the right-hand side. I can modify this. I could make it a sine of omega t on the right-hand side instead of a cosine. I could also have a different amplitude other than 1, like 2 or 3 or whatever. And I did talk about what to do in that context in the last lecture. But we want to just focus on this main kind of special case because it really illustrates all the phenomena that we can see in the more general setting. We are initially here going to consider the damped case. P is positive, not equal to 0. The general solution, YH, of the associated unforced or homogeneous equation, this is the unforced equation where 0 is on the right-hand side, we did talk about in lecture 28, is transient. It decays to 0 as t increases because there's exponential decay factors in the formula for the solution, for YH. In the case where p is 0, it doesn't go to 0, and we'll see that later here. We also talked about in 48a that to find a particular solution of this equation, it's a good idea to complexify the equation. In other words, to replace the cosine of omega t on the right-hand side with e to the I omega t on the right-hand side that you see right here. That's called the complexified equation. It's not the same as the original. It's a different equation. But having an exponential on the right-hand side then inspires us to guess an exponential solution, and then through Euler's identity and ultimately taking the real part of the complex solution, we get a solution of the original, almost like magic. We take the real part when the right-hand side is the cosine function. You end up taking the imaginary part when the right-hand side is the sine function. Yes, guess a complex solution. Call it y sub c, c for complex, is a e to the I omega t, where a is the undetermined coefficient, which is going to be a complex number in general, that we need to solve for. What ended up happening in lecture 28? I'm not showing you the details here in lecture 29. When we solved for a, we got this complex number, ultimately, that we could write like this. A pretty complicated looking thing. I mean, you shouldn't expect it to be too easy. This is a pretty general kind of equation here. This quantity is called the real part of A. I'm also labeling it B in these lectures. And this part, including the minus sign that's next to the I, is called the imaginary part of A. Again, both the real part of A and the imaginary part are real numbers. It's just that the imaginary part is next to the I. I will also let C equal the imaginary part, including that negative sign. And in the complex plane, what's going to happen here, we are going to want to think about pictures of where this constant A is in the complex plane, where the horizontal axis is labeled with the word real, and the vertical axis is labeled with the word imaginary. The imaginary part is always going to be negative for us. P is positive, omega is positive. We're dividing by a positive number. The real part could be positive or negative depending on the sign of the numerator, whether q is bigger than omega squared or not. What that's going to mean is this number a in this complex plane, when we're thinking about plotting it in rectangular coordinates, will be down below the imaginary axis somewhere where the imaginary part is negative. Okay, that's a helpful thing to realize as we continue going through this. Amazingly, this is a pretty cool thing and part of the motivation for using complex arithmetic. This complex number a, in almost a magical kind of way, ends up encoding both the amplitude, capital A, and the so-called phase angle, phi is a number, not a function here, when, at least in the case of a cosine forcing function like we have, the forced response, the steady state solution, the yp, the original, the particular solution of the original equation, can be written in this way. Yp, as I said, would be the real part of yc. You could replace a with what you see there and multiply times e to the I omega t, which by Euler's identity is cos omega t plus I sine omega t. The real part ends up equaling this. I did talk about that in the last lecture, where b is this quantity and negative c is the opposite of the quantity I circled there. So actually negative c is a positive number. And that can be written as an amplitude capital A times cosine of omega t plus phi. And when you add that quantity phi in there like that, that is called a phase angle. Okay? Why does this happen? I'll tell you here in a minute. It turns out that capital A, the amplitude, if, for example, little a happens to be right here with complex real and imaginary parts b and c, c is going to be negative. Capital A is the distance between little a and the origin. And phi, the phase angle, is going to be this angle right there, taken as a negative angle. And so really when we add phi, we're really subtracting a positive number. And phi is going to be related to a certain rightward shift of the graph. How do we know we can write it this way? It's because A itself can be written in what's called polar form. It can be written as its distance to the origin, written as the absolute value of A, and often called the modulus of A, times e to the I phi, where phi is this angle. Why does this happen? It's essentially polar coordinates. By Euler's identity, this is the same as the absolute value of A, the distance of A from the origin, times cosine of phi, plus I times the absolute value of A, times sine phi. That's Euler's identity, and these then are essentially the polar coordinates of this point. And now, coming back up here to yc, yc is A e to the I omega t. Replace A with its polar form, its absolute value, again, or modulus, times e to the I times phi, times e to the I omega t. And now use a property of exponents to combine these e's. I'm going to go ahead and put it up here. Yc will be the absolute value of A, e to the I, omega t plus phi. And if you use Euler's identity once again, you get the absolute value of A, cosine omega t plus phi, plus I times the absolute value of A, sine omega t plus phi. And the real part of that, well, it's not too hard to see here, is this thing right there. That's why we can write it this way. One verification of that. You could also use trigonometric identities to verify it, but it's more fun to do it with the complex numbers. Yes, capital A is the distance between A and the origin in the complex plane, also called the absolute value of A or the modulus of A. It is the square root of b squared plus c squared by the Pythagorean theorem. Because b equals this and c equals this with the minus sign there, although the minus sign goes away when you square it, you can write that like this. Try it. Okay, it's a little complicated looking, although if you derive a in the way we did before, it's a little quicker. That is how the amplitude depends on p, q, and omega. And that's one of our main points of emphasis here in this lecture 29a. Phi is the angle that A makes. This is, I didn't color this one red, I probably should have. That A makes as a vector, or as a ray, if you make a ray going from the origin through little a, with the positive real axis, like I drew over there, written in this way. Phi is sometimes called the argument of A. That is the angle that you see. The angle has to satisfy this equation. Its tangent, essentially by SOHCAHTOA, has to equal this. Essentially taking the imaginary part and dividing it by the real part. When this is defined, when you're not dividing by 0 for one thing, and also we actually can't write this equation when phi equals negative pi over 2 radians, negative 90 degrees, because the tangent function is undefined there. But we could look at the picture and see, in the case where we are on that negative side of the imaginary axis, that phi would be negative pi over 2 in that case. The argument of A, arg A, that's just another name for the angle. Now let's get into our analysis of the amplitude of the force response. Before doing so, let me just briefly remind you that in the damped case, I did say in 28A, solutions of all initial value problems approach the force response called the steady state solution as T increases. That's something you should definitely know. When P is positive, when there's damping, that will happen because of the exponential decays in the YH, like I talked about 5 to 7 minutes ago or so. Right? Steady state solution is the force response. It's not an equilibrium solution. It's not constant. It oscillates. It's a sinusoid. But all other solutions are going to approach it. Here's something new that we didn't talk about last time. It is common and useful to graph the amplitude, capital A, of the force response, the steady state solution, as a function of one or more of its variables, while the others are/is held constant. If we graph it as a function of one of its variables, it's got 3 variables, P, Q, and omega. I can think of those as variables if I want. If I graph it as a function of one of them, just like, for example, omega, then I keep P and Q held constant as I make the graph. If I graph it as a function of more than one of its variables, say P and omega or Q and omega, I'd hold the other quantity constant. Here's an example. Here I'm emphasizing that A, the amplitude, I'm going to think of as a function of omega, where P and Q are constant. I'm going to graph this as a function of omega. Actually, I'm going to show you more than one graph. It's this picture, various graphs of A over omega. I took Q to be 2. So I plugged in Q equals 2 right there in this equation. Plotting it for different values of P. These 3 values of P, 0.1, 0.5, and 1. As P increases, the graph goes from red to blue to pink here. Its maximum height goes down. It's more interesting to think about what happens as P increases. Its maximum height is going up. And what would that mean for a mass on a spring, for example? Or any other situation where you've got a forced harmonic oscillator. We will think about the practical implications of that here in a minute. Do these peaks line up vertically? Almost, it looks like, but not exactly. This one's peak for the red one is a little bit further to the right of the blue one's peak. And the blue one's peak is a little bit further to the right of the pink one's peak, which I'm guessing is maybe around there or so. So the omega critical point for these functions is not the same as P changes, though it does seem like they're close together in value here along the axis. What if I held Q constant and graphed this quantity as a function of P and omega? That would be a multivariable calculus kind of function. I'd want to have the P and the omega axes be horizontal and the A axis be vertical. And as P and omega vary over a plane, essentially, what happens to A? Here's a picture I made with Mathematica. So the P axis is going to the right, or going this way, coming out of the screen at you. That's the P axis. The omega axis is going to the right. That's the positive direction for that. P and omega are positive, so I'm only thinking about graphing this where they are both positive. And the green surface that you see is the output, the height for any given value of P and omega in this plane down here is plotted. You plot a point for that value of p, that value of omega, and then whatever value of a you get here in three-dimensional space with rectangular three-dimensional coordinates. You can do that for lots of different values of p and omega. Again, you get the surface. And notice I colored some curves there, red, blue, and pink. In fact, they're essentially the same curves as this. This first red curve is when p is 0.1, 0.1 being real close to 0 there. The blue one was when p is 0.5. Notice 0.5 is right there. That's matching up with the p coordinate of the points on the blue curve. And then when p is 1. Along that line, I'm graphing the pink curve as omega varies. You might wonder, do these graphs always have a peak as p increases? And you might guess, because of the behavior here, that maybe they don't. Let's go ahead and use some calculus to try to maximize a as a function of omega. Does the maximum value of a of omega occur, for example, at omega equals square root of q? Based on what I said 2 minutes ago, you should say, no, it doesn't. Because it changed as p changed, right? As p decreased, the graph went down and the critical point moved a little bit to the left. So the answer is going to be no. But let's go ahead and see how it depends on p and q anyway. Use calculus. Differentiate this function of omega. In general, a depends on p, q, and omega, so I could write it as a partial derivative. But if I'm thinking of the a function from the previous slide as a function of omega, I can use a prime as well. Treat p and q as constants. Treat omega as the variable. I have to use the chain rule. Bring the negative 1/2 down in front. Subtract 1. Negative 1/2 minus 1 is negative 3/2. Put the entire inside thing still in there. Then, by the chain rule, multiply times the derivative of the inside with respect to omega. I could expand this out, but I didn't bother. I brought down the 2 to get 2 times q minus omega squared to the first. Then, by the chain rule again, multiply by the derivative of the inside here with respect to omega, which is negative 2 omega. That's what you see there. Then, plus the derivative of this with respect to omega. Bring down the 2, you get 2p squared omega. Set this equal to 0, solve for omega. Doesn't look so easy, does it? Well, it's easier than it looks. That's a negative power, so it's like we're dividing by a positive power. It's like this really is a fraction. The only way a fraction can equal 0 is if the numerator is 0. I can cancel the 2's as well. And so I can focus on this thing inside here with the 2's canceled, the 2 that I canceled, equaling 0. Don't cancel this other 2. Then expand this out. Multiply the negative 2 omega through the parentheses here. You're going to get a positive 2 omega cubed. You'll get a negative 2q omega. You still have the p squared omega. You can rewrite it like this at cubic. When it's equal to 0, we're setting it equal to 0 and solving for omega. Omega can be factored out, so one solution is omega equals 0. The other solutions can be found by setting that equal to 0 and solving for omega. You could use the quadratic formula. You don't have to because it doesn't have an omega to the first power term. I can just subtract this from both sides, divide both sides by 2, and then take the square root. If I take the positive square root, I get the positive critical point. You should take the time to check that it's this. That's going to be a real number critical point that's bigger than 0 when 2q is bigger than p squared. It needs to be bigger than 0 for it to truly be positive, because 0 is neither positive nor negative. Okay, is this useful? Let's think about it a little bit. While this does not equal square root of q, it will approach it as p goes to 0 from the right. The plus sign there means from the right. So p is approaching 0 from the right. It's first 1, then 0.1, then 0.01, then 0.001, etc. As p goes to 0, that part goes to 0. This whole thing approaches square root of q. So while it doesn't occur at omega equals square root of q, it does approach it. Now you might be wondering, why is omega equals the square root of q important? Maybe you've realized it, maybe you haven't. I did talk about fast and slow oscillations in the last lecture in the undamped case, and I'll talk about it again here in a few minutes. We had the beat phenomenon occurring when omega was close to square root of q, when the forcing angular frequency is close to the angular frequency of the oscillator itself. And you can actually get rid of the word angular and just say frequency because these are directly proportional to the frequencies. So we're near resonance when omega is near square root of q, so maybe that would be why the amplitude is high when omega is close to square root of q, and that is true as long as p is close to 0. On the other hand, as p approaches square root of 2q from the left, that negative sign means means from the left, through values just less than the square root of 2q, it doesn't mean this is a negative number. This thing's going to approach 0. The thing under the square root is going to approach 0, so the square root itself will approach 0. Omega, the positive critical point, will get closer to 0. We saw in the picture it moved to the left as p increased. It didn't look like it was necessarily going to 0 in the picture, but it does end up going to 0. And when 2q is less than p squared, then you only have one critical point at the origin. Evidently, when p is bigger than the square root of 2q, where your one critical point is at the origin, then this function does not have a maximum. And evidently, if we look at the graphs, it's going to be a strictly decreasing function of omega in that case. What are the practical implications of all this? I will show you Mathematica to illustrate those practical implications. By the way, this one I'm going to show you right now is an animated version of the graph I showed you before. As p goes to 0, you can see p is decreasing there towards 0. This graph gets large very rapidly, and it's very large. It's got a very high peak, a very sharp peak as well, when p is small. Near omega equals square root of q. Q is 2 in this example, so square root of q is about 1.4. This peak is close to 1.4, though not exactly equal to it. What is this telling you? This is the damped case, not the undamped case. There is a bit of damping, a bit of friction. So the solutions can't explode to infinity, but they can get high in amplitude. In fact, the steady state can get high in amplitude. Remember the steady state, the forced response, is a sinusoid wave of a certain amplitude, certain period, a certain shift related to the phase angle. This is saying when omega is close to about 1.4 here, the forcing frequency is close to the resonant frequency of square root of q. That forced response has a high amplitude, close to 8. As omega moves away from 1.4 or so, that amplitude does decrease pretty rapidly when p is small. You should expect a large forced response, which all solutions approach as t goes to infinity, when omega is close to square root of 2 in this case. And it gets more pronounced when p is small, when the damping is small. On the other hand, when the damping is relatively large, we still get a maximum amplitude for the forced response, a maximum energy, if you want to think of it that way, when you're close to the peak here, which is a little less than 1.4, 1.3 maybe. You still get a maximum, but it's not as extreme when you've got more damping. Down here, I got another way to think about it here. Ignore this graph for the moment. Just focus on the relationship between these two graphs. When p is relatively large, I'm taking omega to be 0.2 here. That is the forcing function's angular frequency. The blue graph is the forced response. Its amplitude, you can see, is maybe in the ballpark of 0.3 or something. As omega increases, which corresponds to a higher frequency forcing function, we are approaching a maximum amplitude for the forced response. But it's not very pronounced unless p gets smaller. As p gets smaller, you can see that amplitude gets higher. So different p's are different amounts of damping and different amounts of friction. Different omegas are different frequencies for the forcing function. These are different situations. You can see for small omega, the force response does not have a very high amplitude. For large omega, it doesn't have a very high amplitude, but for some intermediate value, it's got a maximum amplitude somewhere close to here or so. Okay, and it gets more pronounced again as the damping gets low. When you've got a low amount of damping, low friction, you have to be aware of the possibility of high amplitude responses. That would be bad if you're thinking about, for example, shock absorbers in a car. Or maybe your bridge that you've just constructed oscillating too much in the wind. Here's another new thing related to that other graph. It's also common to graph the phase angle phi of the force response as a function of one or more of the variables, p, q, and omega, while the others or other r/is held constant. With a caveat, if we're going to find a formula for phi, it's got to be an expanded inverse tangent function to find it. Remember, tangent of phi was negative p omega over, I think it was q minus omega squared, so phi should be the inverse tangent of that. But remember, the inverse tangent gives you outputs between negative pi over 2 and positive pi over 2, but we want our angle to be down here between between 0 and negative pi, actually. And because of that, it's a bit tricky to come up with a formula for phi as a function of p, q, and omega. I will show you how I did it on Mathematica, but here's, I'm going to go ahead and write the inverse tangent function, but just keep in mind that this is a more extended kind of inverse tangent function, giving us an angle in the third or fourth quadrant, phi being between 0 and negative pi radians. Here's what the graphs look like when q is 2 for different values of p. I'm expanding the number of p's that I'm choosing. By the way, this does match the graphs in the Blanchard, Devaney, and Hall book that we use, if you happen to have that book or if you're my student. Interesting. These graphs are all decreasing. Some of them have inflection points and some don't. The red, blue, and pink all have inflection points. The cyan and orange do not have inflection points. They all do seem to go through this point. The second coordinate of that point is actually negative pi over 2, negative 90 degrees. What's the first point? Is it possibly square root of q? Looks like it might be. It's close to 1.4. And likewise, we could also graph as a function of p and omega, a three-dimensional graph that looks like this. And once again, I've sliced the graph at different values of p to match these graphs. These two pictures are related to each other. And they're both interesting to think about. What are the practical implications of this? We can go back to the same part of the Mathematica document here, right here. I've got the phi as a function of omega here, where p and q are fixed. I'm taking, again, q to be 2. And I'm letting p change and omega change. Watch what happens here. So we're thinking about the force response. This blue graph, which is the actual oscillation or long-term oscillation of the oscillator. Again, the value on this graph gives you the amplitude, the second coordinate of that black dot, at this value of omega, 0.2, gives you the amplitude of the blue graph. This gives you the phase angle, which is a small negative number. What does that mean? Remember, the phase angle essentially represents a rightward shift. Its absolute value is the amount of the rightward shift as a fraction of a period. So when phi is, for example, pi over 2, or negative pi over 2 in this graph, watch the blue graph shift to the right as well as increase in amplitude. Its peak at t equals 0 its first peak, its first high point is close to t equals 0 here when the phase angle is a small negative angle. But when the phase angle is bigger, negative angle like negative pi over 2, somewhere right around there, now when t is 0, we're not at the peak. We're at the average value of the blue graph. The blue graph, if it had been starting at the peak when t is 0, has been shifted to the right, how much? By 1/4 of a period. Just like negative pi over 2 is 1/4 of the way around the circle. As I continue increasing omega, the blue graph decreases in amplitude again, but now the phase angle approaches negative pi, and the peak has shifted even further to the right as a fraction of a period. It's close to half a period to the right actually now, because it looks like the low point of the graph at t is close to t equals 0 here. And it gets more extreme as omega gets even larger, though now the oscillations are so small it's hard to tell, but at t equals 0 it is close to starting at its low point now. We've shifted 1/2 period to the right. That does have implications for the actual oscillator, the mass of the spring, or sound waves, and sound waves causing a goblet to vibrate and maybe break, like when a singer sings a certain note. This is all related to practical things. Let's also review the undamped case pretty quickly. And then our final thing about oscillators is going to be about the resonance case. I'm going to go through these slides quickly because I do want to get to the linearization also of the nonlinear system, the van der Pol equation. In the undamped case, which we also looked at in lecture 28a, p is 0, we observe the beat phenomenon, or the beating phenomenon, near resonance when the forcing and natural frequencies are close but not equal. We got this kind of picture in lecture 28a. This is the beating phenomenon. There's a fast oscillation with a high frequency and a relatively low period, and a slow oscillation. You want to think of the slow oscillation as having a period obtained by going up, then back down, then back up, say. That would effectively be one period of the slow oscillation, and the reciprocal of that number, which is 80-something, would be the frequency. And if time is in seconds, the frequency would be in cycles per seconds, which we call hertz. I derived formulas using some fancy complex arithmetic for the period and frequency of both the slow and the fast oscillations. I'm going to show them to you again, and then I'm going to show you the numerical values as well when omega is 1.56 and q is 2. So square root of q is square root of 2, which is close to 1.4. For this graph that you see here, the period of the slow oscillation is about 80-something, 86.2 seconds, if time is in seconds. Its frequency is its reciprocal, 0.012 hertz, a very small number of cycles per second, 1.2% of a cycle per second for the slow oscillation. For the fast oscillation, the period is 4.2. The horizontal distance peak to peak is 4.2 approximately. And the frequency is the reciprocal of that, still less than 1, so you could still say it's a small frequency compared to, for example, sound waves that you can actually hear. But that would be what it is, the frequency, the reciprocal of the period. Go ahead and take the time to check these numbers. And again, for real-life applications, like sound waves and typical kind of sound waves that people can hear, like playing on scales on the piano, for example, your sound waves are in the range of hundreds of hertz cycles per second. And so the period is one over those things, which are, the periods are really small numbers. But on appropriate scales, you can still get this kind of phenomenon, and that it will occur when you've got, for example, two tuning forks whose natural frequencies are very close together, but not equal, slightly different notes, and you can get this beating phenomenon. What happens at resonance? Again, I'm going to go quickly. At resonance, in the undamped case, that happens when omega equals square root of q. You have to modify your guess for the complex solution. You have to add an extra factor of t in there for the complexified equation. For that complexified equation, I went ahead and replaced omega with square root of q there. You have to do that. Okay, I'm not going to explain it. You should go ahead and take the time to check it. adding the extra factor of t is necessary. If you don't have there, it won't work. It won't be a solution. In the end, for generic initial conditions, after figuring out what A is, using Euler's identity to expand this in terms of real and imaginary part, taking the real part, adding it to the general solution of the associated unforced equation, the YH, before solving your initial value problem, you get this formula. I got this from Mathematica. And the most important thing about this is not necessarily the formula itself, but to notice that in this formula you have a t term multiplied by the sign that's going to cause the graph of this to blow up as t increases. The oscillations are going to get bigger and bigger. They're still fast oscillations with a large frequency in a small period, say, but the slow oscillation has infinite period. So you go off to infinity. Slow oscillation has infinite period and essentially zero frequency because it doesn't come back down again. This corresponds to at least approximately a drinking glass breaking when a powerful singer hits just the right note. Okay? It's not perfect because in real life things do have damping. Damping is positive. But the idea is this might be a decent approximation if the damping is very, very, very low. It's sometimes something engineers seek to typically avoid in situations where the oscillations can be forced and it might be dangerous, like car oscillations as you go over a road, building oscillations in the wind or in an earthquake, bridges oscillating in the wind or during an earthquake. That's something that you want to avoid as an engineer. All right, a little bit more here for lecture A. I also want to introduce nonlinear systems. I want to analyze nonlinear systems. Two main tools, one of which we already know about is null-clines. A second of which we already know about in the one-dimensional case back from chapter 1 is linearization. The linearization is the part that gets a lot different than what we've done so far. The null-clines for a nonlinear system are more complicated than linear system null-clines, but the idea is still the same, at least when you're talking two-dimensional problems. Let's think of this in the context of the van der Pol equation. As a second-order nonlinear ODE, we wrote it this way. We set up modeled certain kinds of electric circuits. What's the corresponding first-order nonlinear system or vector field? It's this. I define y to be dx dt to get the first component. And once y is defined to be dx dt, I can find dy dt, which is going to be the second derivative of x with respect to t, and solve for that in terms of x and y, really. This is a y right there. And you get this on the right-hand side. You can multiply the negative epsilon and the y through the parentheses and write it like this. And then you could separate this into a linear part, where x and y are to the first power, and a nonlinear part. The epsilon parameter goes in both terms. That's saying what epsilon represents. It's just a constant greater than or equal to 0. This is the linear part, this is the nonlinear part. In general, nonlinear equations like this, you cannot find the solutions except maybe in very special cases like equilibrium points, for example. Here's a picture of the phase plane when epsilon equals 1. We looked at this picture before, back, I don't know, lecture 10 to 15 lectures ago. This one right here is the van der Pol phase plane root. We were talking about using Euler's method to help us approximate solutions. We have the null-clines, the brown null-cline. My coloring is different here than what I've done recently. The brown curves are the y null-cline, and the green line, the x-axis, is the x null-cline, so that's a different coloring scheme than I've used more recently. And we saw that this particular system seems to have a periodic solution that comes back to where it starts and looks approximately like this. We approximated it with Euler's identity. Okay? Also, notice something else. The origin is the only equilibrium point. That's where the brown and green intersect at just one point. Also notice it looks like the origin is a spiral source. Solutions are moving away from it, at least when you're close to it as t increases. If you're further away, solutions kind of go toward the origin, but they get stopped by that periodic solution, that limit cycle. But if you start close to the origin, you spiral away. It's like the origin is a spiral source, at least locally, near the origin. Linearization in calculus is all about local behavior. That's why linearization is going to be helpful here. What does it mean to linearize this nonlinear system? At or near the equilibrium point, which is at the origin. That's the unique equilibrium point. What does that mean? It means to discard its nonlinear terms. In other words, ignore them. Pretend they're not there. Wait, isn't that cheating? Well, it's not, as long as you only care about the behavior of the system near the origin and you don't care about that periodic solution and you don't care about solutions outside the periodic solution. You're just focused near the origin. It is a different system. It's a linear system, whereas van der Waals is nonlinear, but it's related. We always have these associated or corresponding equations that are related to our original ones. It's a very good technique to be able to use that. What is the corresponding linearized system then? If I get rid of that nonlinear part, I'm about to show you the equations. I have some extra notation in here that's a little confusing. I'm going to write it this way. dy dt is dx dt dy dt. Focus first on this. That is the linear part in the preceding slide. For the full van der Waals equation, we also added on the nonlinear part to that, but now I'm ignoring the nonlinear part. I only have first powers of x and y, or zeroth powers, because there's no x in the first one. This can be, as a linear system, a linear vector field, it can be written as a matrix times a vector. What's this other stuff with the L and the J? L sub epsilon of y, pretend epsilon is fixed, is a linear transformation, really. A linear vector field. L is the name of the function. L for linear. I could have called it T, like I've often called linear transformations. Decided to call it L. This is going to make a clearer connection to calculus, Calc 1, in fact. What's this thing? J epsilon 0, 0. J stands for Jacobian matrix. Jacobian matrix. And the 0, 0 stands for the fact that I'm evaluating that Jacobian matrix at the point 0, 0, which is the equilibrium point at the origin. Again, the epsilon is just a constant, don't worry about it. This whole thing, well, I should maybe circle the whole thing. This whole thing represents the Jacobian matrix, which is this matrix right here. A linear transformation is defined by a matrix multiplication, as always, in Rn at least, or in this case, R2. It's in honor of somebody named Jacobi. It's actually not consistent notation. Some people use a D there instead. The D is not named after anybody. D stands for derivative. This is a kind of derivative of the nonlinear system in ways I'll explain very soon, not in this lecture. For the phase plane in the previous slide, when epsilon is 1, the trace of this matrix, T is the trace, 0 plus epsilon is epsilon, which I'm taking to be 1, it's positive, and D is the determinant. I'm thinking about the trace determinant plane here. I'm wondering how to classify the origin for this nonlinear system based on the trace determinant plane. I could also think about the eigenvalues, but as far as the trace determinant plane goes, t squared over 4 is less than d. D is bigger than t squared over 4. In the TD plane, with the 3 critical loci, the t-axis where d is 0, the positive d-axis where t is 0 and d is positive, and the repeated root parabola, whose equation was d equals t squared over 4. Since d is bigger than t squared over 4, we are above the repeated root parabola. Eigenvalues are complex numbers, non-real complex numbers. And because these t is positive, We're on the right side of the d-axis, and that's where we had spiral sources. The origin is a spiral source. Just like for the nonlinear system on the previous slide, for the van der Pol equation itself, the origin was a spiral source. This is no accident. This will usually be the case. When we linearize a nonlinear system near an equilibrium point, the type of the equilibrium points will match usually. If one's a spiral sink, the other one will be a spiral sink. If one's a spiral source, the other one will be a spiral source. If one's a saddle, the other one will be a saddle. If one's a real sink, at least in the non-repeated eigenvalue case, the other one will be a real sink. What's the case where this doesn't happen? The case where you have a center can be a problem. Where the linearized system has a center, the nonlinear system does not necessarily have a center. And that is the end of lecture A. Thanks for watching.